Honors Geometry students, this is Mr. Hale, and today we're going to look in Chapter 2 at Section 2.5, which is about postulates and proofs. We're going to start with some terminology, and then we're going to move our way into essentially the first proof we've seen. We're going to do it a little bit informally today, but it'll be an introduction. So let's start with some terminology, and actually all this terminology up top is actually review. So the process of observing data, recognizing patterns, and making generalizations from your observations is called inductive reasoning. Inductive reasoning. And again, we studied that earlier in the chapter. That's when you use patterns. Okay, in mathematics, and when you make a generalization, it's called a conjecture. So a conjecture would be something like, hey, I noticed the pattern of the numbers is they're multiplying by 3 every time. So my conjecture would be that that pattern will continue. So multiplying by 3 could be an example of a conjecture. Okay, all we need to prove a conjecture false is a single counter example. A counter example. Now remember, a counter example is just one case where the P part of our statement, the if, is correct, but the Q or the then is false. Okay, so hypothesis true, conclusion false is what a counterexample would be. And again, you only need one to disprove a conjecture. Okay, the process of demonstrating that if certain statements are accepted true, then other statements can be shown to follow from them. This is the other type of reasoning we talked about, which is deductive reasoning. Again, those are both repeats from our 2122 notes. Really all this terminology is. Okay, a little more terminology, not a lot for us to write down, but just some explanations here. A proof is needed to show that a conjecture is true. So we can't just accept conjectures until we've used the process of formal proof. And a proof is one form of deductive reasoning. It's using essentially a combination of statements that are known to be true to show that another statement is true. A proof of an if-then statement is a sequence of justified conclusions leading from hypothesis P to conclusion Q. And each geometric conclusion is justified by definitions, postulates, algebraic properties, we'll study those in a bit, or previously proven theorems. So once you've proven a theorem, you can actually use it later on. Now there are 3 types of proofs that we'll study. Paragraph proofs are kind of just written out in words. 2 columns are sort of the standard for formal proof, which we'll look at that, but essentially you always have statements and reasons on every step. And then the flowchart proof, I kind of like those. It's more of a visual proof that it still has statements and reasons, but it shows the connection, in my opinion, a little more clearly. Okay, proofs will always have 5 parts. There'll be a diagram labeled with known information. Then there'll be a part of it that says given. And so you have given information. You have to start with some known info. And then when it says prove, that's essentially where we're trying to get to. So the given is essentially connected to the if, where the prove would be the then. So we're trying to get there. And then we have a list of statements, that's generally what we do, and then reasons which explain each of those statements, okay? So there are 5 steps, like you can see here. You'll start to make sense of it, and due to the course of this year, we're not gonna go quite as in depth this year as we do some years, but I think you guys will still get a pretty good taste. All right, so we're gonna write a deductive argument for the following conditional. If angle ADC is a right angle, then angles 1 and 2 are complementary. Here's what I want you to do actually. Instead of watching me do this, why don't you pause the video in just a second and then just start writing down little snippets of information. What is it how could I go from knowing that angle ADC is a right angle to knowing that 1 and 2 are complementary? So just jot down the things that you kind of know and then come back to the video. So hit pause now. Okay, welcome back. I've written down 4 or 5 statements here that kind of connect us from our if to our then. And it's not done very formally, but here are some things we might have noticed based on the diagram and the given information. So it says ADC is a right angle, and it would honestly probably be smart to go ahead and mark that over here, right angle. Okay, then 1 and 2 are complementary. All right, well, let's think about how we would go from the if to the then. Well, first of all, we know that right angles measure 90 degrees. That tells us that angle ADC has to be 90 degrees, just since it says it's a right angle. Okay, the next thing I looked at was that angles 1 and 2 were adjacent angles, and together they form angle ADC. So I could have written that as in a different way of saying, like, measure of angle 1 plus measure of angle 2 is equal to the measure of angle ADC, which, by the way, we know angle ADC is 90 degrees. So then we could go to the last step. That means 1 and 2 have to sum to 90, which makes them complementary. That is our definition of complementary. Okay, now I want to walk you through what this might look like. This looks a lot like what I just wrote down, to be fair. But here is the same proof written in, it's written in a paragraph format. We don't always have the paragraph format numbered like this is, but this one is numbered. It's fine. And this is essentially the logic process that I was just taking you through. If angle ADC is a right angle, then the measure of angle ADC is 90 degrees. Don't lose that degree symbol, kids. All right, because of the definition of right angles. If B is in the interior of angle ADC, then angles 1 and 2 sum to be the measure of angle ADC because of angle addition. I didn't use the word angle addition, but we did that same setup. And again, we know that if angle 1 plus angle 2 is equal to the measure of angle ADC, and the measure of angle ADC is 90, again, degrees. Sorry about that. There we go. Then the measure of angle 1 plus the measure of angle 2 equals 90 degrees because of the transitive property. All right, you guys have seen transitive property. You might be a little rusty on it, but it's just simply if A equals B and B equals C, then A equals C. All right. And then the last step, if measure of angle 1 plus the measure of angle 2 is equal to 90 degrees, we're not going to miss that half point, then angles 1 and 2 are complementary because of the definition of complementary. That's what complementary means. Okay, the last thing we've got for you today is several postulates and theorems. As a matter of fact, I mentioned a postulate up, or a property up here. I'm going to go ahead and write it out for you. I think it's worth adding it in just in case you're a little rusty on this, or if it got COVIDed. Is that a word? All right, I don't know. But if A equals B and B equals C, then A equals C. It's sort of just a logical process. I think it probably makes common sense to you. All right, last thing we're going to look at today is some postulates and theorems. These are things just to kind of add to your toolbox. We'll begin kind of assembling a place to keep these together. But for now, the intersecting lines postulate tells us that the intersection of two lines is a point. Now, if there are two distinct lines, maybe should be included there, because technically two lines could be coinciding or the same line, but then they would be just, I'm going down a rabbit hole. Never mind. All right. Next, on intersecting planes postulate. If two planes intersect, their intersection is always a line. Okay. Imagine two walls meeting in the room that you're in. Where they meet, if they extended infinitely, would be a line. All right, the line postulate says that through any 2 points, there is exactly one line. So we could say that a different way and say a line contains at least 2 points. Again, even if the line is not physically drawn on your diagram, it's still there. At least it could potentially be there. That's why when we talk about terms like collinear, we always have to have at least 3 points because 2 points are always collinear. Up next, the plane postulate. Through any 3 non-collinear points, there is exactly one plane, and a plane must contain at least 3 points. All right, so again, sort of like how lines, we have to have 2 points. With a plane, we have to have 3 points to be able to define it. All right, and again, any 3 points, as long as they're not in a straight line, all 3 of them, then they would form a plane. Okay, the 2 more. The flat plane postulate, if 2 points are in a plane, then the line containing those points is also in the plane, sort of a little common sense thing there. We've seen some visuals of that already. And then another one that we've actually already done in this class, the midpoint theorem. If M is the midpoint of segment AB, then segment AM is congruent to segment MB. All right, folks, I know this is a quick intro to what we're going to do with proofs. I hope this makes sense to you, and you guys have a fabulous day.